Okay, so this is about computing definite integrals over so-called infinite intervals of integration. And there's a lot of applications to economics, because basically, usually we want to compute what is called the present value of a flow in continuous time. And at each point in time, the element of this flow is multiplied by a discount factor. So very typically, we have integrals in which we have to compute integrals by parts. One of the two factors is exponential of minus some function of x. And these integrals are extended to infinite intervals of integration, okay? So from now to plus infinity, from now to a point in time in the future, which is very, very far in the future, okay? So you will see an example in a moment. Okay, so basically, in order to compute these integrals, we just have to consider a function which is continuous, and a definite integral over some interval between a, from a to b, okay? Okay, so the touchpad is not very, okay, from a to b, and what is the meaning of this notation? The integral between a and infinity of f of x dx. It's like having the upper limit of integration, which is plus infinity, instead of just being b, a number, okay? This just has to interpret it in the sense of a limit. It is like the integral between a and b, but b is an upper limit of integration that tends to plus infinity, okay? So in principle, we should first compute the integral between a and b, and then let b tend to infinity and see what happens. Okay, so this is the basic idea. Provided that the limit exists and is a finite number, of course, in the sense of limits. I mean, the limit must be a finite number in order to be a limit, okay? Not plus infinity. Okay, so and in a very similar manner, the integral between minus infinity and b is like the integral between a and b, but the lower limit of integration a tends to minus infinity. The second one, this one is not really important in economic applications, but the first one, as b tends to plus infinity, is really important. So just, first of all, become familiar with the notation, okay? And with the meaning of this integral. Of course, writing this makes sense only if the limit exists. I mean, in principle, we cannot write the integral between a and plus infinity of f of x dx if the limit doesn't exist, okay? So we can write this, it is a well-defined quantity only if the limit exists. Okay. The basic example is that of the power function. Suppose that we want to compute the integral between 1 and infinity, where infinity is, if we don't put the sign, is plus infinity, of course, of x to the power of minus a dx. Okay, you can hear me, right? I don't need this one. Can you hear me? Okay. And I hope that, no, because this should work for students at home, right? I guess. Okay, there is an important insight here already, because all the elementary power functions, remember the first class last September, all the elementary power functions of the type f of x is equal to x to the power of minus alpha, where alpha is positive, which means x raised to a negative exponent, okay, real exponent, have all qualitatively similar graphs over the interval between 0 and plus infinity. Okay? All qualitatively similar graphs because the graph is like this. It's kind of similar to a branch of hyperbola. Okay? As x tends to 0, the graph tends to the vertical asymptote to plus infinity, basically. As x tends to infinity, the graph tends to 0. All have the same graph qualitatively. The only difference is, let's say, the speed with which this branch of the graph approaches 0. Some of them are slower and some are faster. The larger is the exponent alpha, the faster is the convergence to 0 of this branch. Okay, it approaches 0. It is faster in approaching 0. Suppose that you want to compute the integral between 1 and infinity of x to the power of minus alpha dx. In principle, we want to compute this area between the curve, the horizontal axis, starting from 1 and up to plus infinity. Okay? It's quite intuitive that if this branch approaches 0 very quickly, it should be possible to compute that area. But if the convergence to 0 is slower, it's likely to be impossible to compute that area. Okay? I mean, when you increase x, you add a small piece of this area. Okay? You add a small piece to this area. If these pieces that you add by increasing x become smaller and smaller sufficiently fast, then your area converges to a finite number. But if they become smaller and smaller, of course, but not fast enough, the process doesn't converge. So you cannot compute the area, a well-defined area. So basically, in the limit, you see that it is plus infinity. It's not a number. So what is the threshold between being able and not being able to compute the area? The threshold is alpha equal to 1. If alpha is larger than 1 here, for instance, x to the power of minus 2, then you can compute that area. But if alpha is 1 or smaller than 1, yet negative, but smaller than 1, minus alpha is negative, but alpha is smaller than 1 or 1, you cannot compute the area. So the threshold is 1, okay? And we can see it very easily if we apply the definition of this, this limit, okay? Because first we compute the integral between a and b of that quantity, and then we take the limit as b tends to infinity. And we see it very clearly that the threshold is 1. Why is that? Because if we compute this integral, this is an elementary integral, it's minus alpha plus 1 at the new exponent here, divided by minus alpha plus 1, and this is a primitive of this function, and we have to compute this primitive in b, and then subtract the value in 1, okay? The primitive computed in b is it's b to the power of 1 minus alpha, and computed in 1 is just 1, okay? So we get this primitive. Then we can just change the sign here and here, just to have a more friendly notation here. 1 over alpha minus 1 times 1 minus b to the power of 1 minus alpha. Now, suppose that alpha is larger than 1, for instance. So instead of having a negative exponent here, you can put this in the denominator, okay? Though this is more intuitive, because now suppose that alpha is larger than 1 for a moment. You have b, which is typically, remember that here you have to compute from 1 to b, and then to let b go to plus infinity. B is larger than 1, so b is positive, okay? B is a positive number. To the power of alpha minus 1, which is a positive exponent, what happens to the denominator here as b tends to infinity? it goes to plus infinity. Okay? So this part here disappears, and you are left with 1 over alpha minus 1 as the limit. This is a positive finite number, because alpha is larger than 1. If alpha is equal to 1, you cannot use this formula to compute the integral, because it's the case of the log. We see it in a moment. But if alpha is less than 1, what happens here? Now it is 1 minus alpha, which is positive. So here you have something that goes to infinity. Okay? So you don't have a finite limit for this area as p tends to infinity. So this, applied the definition, shows that the only case in which you have an area that converges to a finite number is when alpha is larger than 1. Here you see that when alpha is smaller than 1, for instance, 1/2, okay? We would have here 1 over the square root of x. Qualitative graph is similar to this one, but the area doesn't converge. And the only case which is left for our analysis is when alpha is exactly equal to 1, so the function is this one, x to the power of minus 1. Its primitive is the log of x. Between 1 and b means the log of b minus the log of 1, which is the log of b, because the log of 1 is 0. Take the limit as b tends to infinity of the log of b is plus infinity. So it doesn't work with alpha equal to 1, it doesn't work with alpha between 0 and 1, it works only when alpha is larger than 1. Okay? So this is the basic insight from power functions. So not all power functions of this type with alpha positive and a negative exponent, then not all functions of this type have a finite area, let's say, when I compute the integral between 1 and infinity. Only those with alpha larger than 1. Okay. For instance, in this case, we have an example with alpha equal to 3 over 2, which means computing the integral between 1 and plus infinity of 1 over the square root of x to the power of 3 dx. Okay? I can use the formula already ready to use because we derived it in the general case, because the general case not only tells us that the limit exists, but also tells us that the value of the limit is this one, 1 over alpha minus 1. So the integral between 1 and infinity of x to the power minus 3 over 2 dx is 1 over 3 over 2 minus 1, which is equal to 2. Okay? So for instance, suppose that you don't remember the formula. You have to compute the integral like this. For instance, okay? We know already that there is a convergence to some finite value here because alpha is larger than 1. Okay, but let's compute our integral. We have to find a primitive. I apply the step-by-step method first. We have to compute a primitive which is minus 1 over x. Okay? It's minus 1 over x. This must be evaluated between 1 and b, and then I have to take the limit of this as b tends to infinity. Okay? So it is minus 1 over b plus 1. So it would be minus 1, okay, plus 1. Okay, and the limit here is, as b tends to infinity, you have here minus 1 over something that tends to infinity, it becomes 0, okay? This is equal to 1. In practice, we don't do that. We don't do this step. We don't write the limit when we show the computations of this. We just write something like this. Once we have found a primitive, we evaluate the primitive directly between 1 and infinity, which means that, of course, I cannot replace infinity here. This means implicitly that I have to compute the limit as x tends to infinity, okay? But the limit as x tends to infinity is just 0 minus 1, which is 1, okay? Clear? Now suppose that you want to, of course, the property of additivity with respect to the interval of integration holds also in this case. So for instance, if you have this function, suppose that this function is our y equal to 1 over x squared. I want to compute the integral between 1/2 and plus infinity. And then I want to compute the integral between 1 and plus infinity, which is the double shaded area, okay? Clearly, this is just an example, but clearly the integral between 1/2 and 2, and 1, the integral between 1/2 and 1 of 1 over of x to the power minus 2 dx can be regarded as the integral between 1/2 and plus infinity minus the integral between 1 and plus infinity, okay? Because this has the meaning of an area, even if it lies below a branch that goes, I mean, it is not a finite area, okay? But you can regard this area here as the difference between the area from 1/2 to plus infinity and the area from 1 to plus infinity, okay? So you can write that it is the difference between the integral between 1/2 and infinity of x to the power minus 2 dx and the integral between 1 and infinity of x to the power minus 2 dx. What I mean, and this property of additivity of areas, which means it is called technically additive property with respect to the interval of integration, holds also in the case of infinite intervals, okay? You can, I mean, if you don't believe it, just compute this integral, make the difference, and you will get the integral between 1/2 and 1 of the same function, okay? So it's a useful, it is also a useful exercise. So when we don't have convergence, we cannot write something like this, because it is not a well-defined quantity. Okay, so now we have an example with a very simple example that has also an economic interpretation. Suppose that you want to compute the integral between 0 and capital T. Now my variable T is, ideally it is time, okay? So from time 0 to some time horizon capital T of exponential of minus 0.05 t dt. So what is the meaning of this? You can regard this as 1 times exponential of minus 5% t, okay? In this case, we have a flow, for instance, a flow of money, of income, with a very simple structure. It is constant at the level 1, which means 1 unit per year, okay? 1 unit, monetary unit, per unit time. It depends on what is the unit time in which you measure t, okay? Usually year. So it is 1 here means €1 per year. If I have 100 here, it's 100 euros per year. But it is uniformly distributed over the year, technically speaking. So if I have €1 per year, I have 0.5 euros every 6 months, 0.25 euros every 3 months, and so on and so forth. So this €1 per year is uniformly distributed over the year. So it is a flow, okay? It's like having a small piece, or a small part of this euro for every sub-period, ideally, with sub-periods that have a length that goes to 0, very short, daily, for instance. So it's like having €1 divided by 360 per day, okay? It's like this. So it is a flow. And each of these is then discounted with this. This is called discount factor. A typical expression for this discount factor is the exponential of minus some interest rate. This is 0.05, for instance, times t. What is the meaning of multiplying this 1 by this factor? The meaning is that if this €1 is immediately, okay, it has to be multiplied by 1. So its present value is the same as its nominal value, okay? But if I have €1 which becomes available in 1 year, so its present value is smaller, okay? It is multiplied by a factor that reduces its value, and the value is reduced, the reduction is larger for larger t. So the same euro in 2 years is worth less than the same euro in 1 year, okay? This is the basic idea. This is called discount factor. So basically, apart from this interpretation, this is the integral between 0 and capital T of a constant flow, unit flow in this case, times a discount factor, which is a function of time, of course, dt, a primitive of this one. Since this is 1/20, a primitive is minus 20 times exponential of minus 1/20t, which must be evaluated between 0 and t, and becomes minus 20 times, replace capital T here, and then subtract 0, replaced here. Exponential of 0 is 1, so you get this, but of course remember that this is smaller than 1, so we can just put 20 here and put a positive quantity into the brackets. So this is the result, okay? So the present value of a constant flow of €1 over a time horizon of 10 or t equal to 10, for instance, years, is 20 times 1 minus exponential of 0.05 times, for instance, 10 years, okay, times 10. What is the integral between 0 and infinity of this quantity? If you have the integral between 0 and infinity, you just have to let t, capital T, go to infinity in this one, in this expression, okay? If t goes to infinity, exponential, you know that the exponential of minus some argument becomes closer and closer to 0 as the exponent increases because it has a negative sign, okay? So this goes to 0 and the result is 20. So what is the interpretation? So for instance, in the first example here, if t is for instance 20 years, you have a constant flow of €1 per year, equally distributed over the year, but €1 per year, okay? Over 20 years, what is the present value of the 5% rate? It is only 12.64 euros. So it is not 20 euros. 20 euros is the nominal value of all the 20 euros over the 20 years. But it is depending on the date where these euros become available, they are discounted. Okay, so the total aggregated value of the discounted sum is this one. And if the flow lasts forever, which is the meaning of taking this limit, one would say, okay, it's infinitely many euros. No, infinitely many euros is the nominal value. The present value is just 20 euros. Okay. So what really matters is basically the last few decades, okay, in this kind of computation. And of course, the result depends on the rate, on the interest rate, because if the larger is the interest rate, the smaller is the result. And the smaller is the interest rate, the larger is the result, okay? The interest rate is the discount rate that you put here. It can be a meaning of interest rate because it is like a kind of alternative opportunity to invest this money, okay? If the value of this flow, if the interest rate is just 1%, the present value of this flow is larger, okay? If the interest rate is 5%, the present value of this flow is smaller. Because if the interest rate is 5%, I have, let's say, outside options to invest this money at the 5% in the market, okay? So if I don't invest this money and I discount this money at the 5%, I get a smaller value. So basically there is an inverse relationship between the present value and the discount rate. The larger the discount rate, the smaller is the present value. So basically, this is just the interpretation. And this is the most elementary model of discounting, a constant flow. Here we have 1 euro. If we have 100 euros per year, just compute 100 times exponential minus 5% t, and what you get is the same result multiplied by 100, of course, rescaled over the initial value of the constant level of the flow, okay? So this is the basic example. Okay, so what I explained is just summarized here. Don't worry about that. I mean, if you are interested, here is an interpretation. But what I want to point out is that in general, we have integrals of this type, not one here, like in the previous example, but f of t times exponential minus interest rate times t. So in general, we have f of t because the flow, the intensity of this flow, need not necessarily be constant. The constant flow is the simplest example, okay? But we may have a changing intensity of this flow, for instance, increasing or decreasing over time, or cyclical, okay? So it depends on the type of model, but in any case, the present value is obtained by computing the integral, which remember is a sum, okay? It is a sum between 0 and t of the flow at time t discounted, okay, with this discount factor. So f of t is called the rate of flow, in the sense that f of t times dt, length of time, is the flow over a time interval of length dt. So this is not just, I mean, this is really important, especially if you want then to apply this kind of continuous time models to situations in which you have data that are available at discrete points in time. So having in mind what is the meaning of a continuous time model is important, because so if the flow is the rate of flow is ft, this means that it can change over time, okay? So at the beginning of some year can be 2 units per year, but at the end of the year it can be 5 units per year, okay? So it changes over time, but it is a flow. And this rate of flow means that f of t times delta t is the amount of money that comes in a time interval of length delta t, okay? it is the flow. It's not the flow. It's the amount of money in t plus delta t. F of t, the flow at the beginning of this small interval times the length of the interval. Okay, so this is the bridge between the continuous time model and the discrete time model. So this is per unit rate means per unit time. Do you remember? Rate means per unit time. In fact, if delta t is equal to 1, you have times 1, which is f of t. But if instead of having 1 year, you have 1 month, this is f of t times 1 over 12, okay? So delta t is 1 over 12 here. If it is daily, 1 over 360. So delta t is the length of time in terms of the unit time. Okay, so this is basically the idea of this, what is the idea behind this rate of flow. Okay, now here we have another kind of, let's say, present value computation. Suppose that we have this one. This is, you don't have to interpret this as a present value computation. Just interpret this as an integral. Next time we show you possibly the meaning, but this is an example of another positive function f of t such that the limit as t tends to infinity of the flow is 0. So the flow, the intensity of the flow goes to 0, but the accumulated value of the flow doesn't converge. But the integral between a and infinity of f of t dt does not converge, okay? So having the intensity of the flow going to 0 is just a necessary condition for the sum, okay, of this flow over the life of the flow itself to converge. If you remember in the previous example, we had all functions with the flow converging to 0, but only some of them have an area that properly converges. So having a function that tends to 0 is a necessary condition. As a minimum, if you want to have a convergent area, you must have a function that goes to 0. But this is not enough, okay? It must go to 0 sufficiently fast. So here is another example in which we have a positive function such that the function goes to 0, the flow goes to 0, the intensity of the flow goes to 0, but the accumulated value of the flow does not converge. So this is another important example. I mean, it's the integral is a log of this one because we have 100 divided by 10 plus 0.5 t, and I have to compute the integral between 0 and capital T. So the derivative here is 0.5, so divide 100 by 0.5, which means multiply by 2. And then here we have exactly the derivative of the log of 10 plus 0.5 t, okay? So 200 times the log of, okay, it is 10 plus 0.5 capital T minus log of 10, which means the log of 10 plus 0.5 t over 10, okay, by a property of the logs. This becomes 1, so it's 200 times the log of 1 plus t over 20.
Sorry, Professor, I lost the difference between the notation of capital T and...
Capital T is the variable of integration. Let's call it the running variable, okay? Capital T here is just the upper limit of integration, which we leave as a parameter, because we want it's the length of our time horizon over which we want to compute the accumulated value of this flow. It's very commonly used. I mean, in applications to economics, usually we use when we study dynamics over time, we use T as the running variable and capital T as the time horizon of planner or the decision maker, and often capital T is plus infinity. in the case of planning over an infinite time horizon, okay? But what you see here is that if we let t tend to infinity, we don't have convergence here, okay? Because the log of something that goes to infinity is plus infinity. By the way, this is not a simple power function, but this is basically the power of a linear function of t, okay? So it's like having an exponent alpha equal to 1 here. Not sure you can see the analogy with the basic case, but it's like having 1 or 100 over t. It's not t, it's a linear function of t, but the behavior of the integral as t tends to infinity is the same. So what can discriminate between convergence and divergence is the value of the exponent that you have in the expression at the denominator. In this case, it is 1. It's not enough. It must be larger than 1, okay? It's exactly the same. You can try with 100 divided by 10 plus 0.55 t squared, okay? We can try with this. We can do that. In that case, it converges. Let's do that. And also, I mean, just try, let me finish this example first. Try to always to check whether your result is plausible, which is a very, I mean, if you are interested in just using basic mathematical modeling, very basic in applications, you don't need much theory, only understanding the basic concepts, but becoming able to check your results, I mean, to see immediately if your results make sense or not, okay? For instance, in this case, we have to compute an area below the curve is like this, from 0 to capital T, okay? Try to represent the integrand first. The integrand is like this. As t is to 0, the initial time, it is 100 divided by 10, it is 10. 10. Then clearly it decreases. Why? Because the numerator remains the same and the denominator increases, okay? So it decreases. It has clearly an upper bound, this area. If you want to compute this area, the upper bound of this area is the time horizon, capital T, times 10. Okay? Because it is the area of a rectangle. I mean, my area cannot be larger than the area of this rectangle, okay? The area of this rectangle, for instance, in the case of 10 years time horizon, is 10 by 10, 100. My result for a capital T equal to 10 years, okay? I use this, I put 10 here. This becomes 1/2. This is the log of 3 over 2. I compute, it's 81.09, okay? So it makes sense. It is positive and it is less than 100, which would be the area of this rectangle, okay? So this is based on the elementary geometric interpretation, but it is quite important to perform this kind of check to your result, okay? See whether it makes sense or not. We can also try to compute, for instance, the same integral where the denominator is not this one, but it is this one squared. Okay, so let me do that. Okay, let me clear the page. Okay, so the integral between 0 and capital T of, now my function would be 10 divided by, let's do that, not 110 divided by 1 plus 0.05 t, which is exactly the same as above, but squared, okay? Let me use this one so you don't get confused, okay? 100 divided by 10 plus 0.5 t squared dt. Now, the integrand, of course, it's not an elementary power function, but it is a power function of a linear function of t. And the exponent is negative, of course, because it is in the denominator, and it is larger than 1. Here we have convergence, okay? That will be convergent because it is similar to the basic case. So this is equal to what? I would like to see in the denominator 0.5, so I have 100 divided by 0.5 times the integral between 0 and capital T of 0.5 over 10 plus 0.5 t squared dt, right? Please stop me if you see any mistakes because I'm teaching since late morning, okay? So this becomes 2. What is a primitive of this one? Okay, a primitive, this is the derivative of the function that we have here, which is raised to the power of 2, okay? So it is minus 1 over 10 plus 0.5 t, right? Is that true? It's an almost elementary integral. I remember a slide after the elementary power functions. A part of the class was called almost elementary functions, which is basically power functions or exponential functions, not of x, but of a linear function of x. Okay, and this is the case. If you're not convinced, just compute the derivative of this. It's minus 1 over this squared times the derivative of this, which is 0.5. So we get this one. Again. And I must compute this between 0 and capital T. Capital T is the time horizon. So this becomes equal to 2. That multiplies.
Should still be 200, I think.
200, sorry, 200. Is 1 over 0.5 is 2 times 100 is 200 actually. Okay, so 200 minus 1 over 10 plus 0.5 capital T. And then when t is 0, this becomes 0 plus 1 over 10. This is not, okay, this is a parenthesis. Okay? Which is equal to, okay, remember now that this 1 over 10 is larger than this one, okay? Okay, plus 1 over 10, so it is larger, so I put this first. So I can do that, 200 times 1 over 10 minus 1 over 10 plus 0.5 t, okay? So this is the result, basically. And now, of course, what is the basic difference? Is that in the result, the capital T is in the denominator here, not as before in the nominator. Okay. Here, the capital T is in the nominator. So when you let capital T go to infinity, there is no convergence here. Clear? But in this case, we do have convergence because the integral between 0 and plus infinity of 100 divided by 10 plus 0.5 t squared dt is just equal to 200 divided by 10 because this becomes 0. As t goes to infinity, the denominator goes to infinity, this ratio goes to 0 and you have 20. 200 divided by 10. I think this should be clear enough. It's all based on the properties of power function, and it's called the asymptotic properties of power functions of this type with a negative exponent, okay? Okay. Okay, this is probably the most difficult example of today's class. And then we see some more examples which are easier, however. Okay, so suppose that you want to compute the integral of, now we have a flow which is linearly increasing. So in principle, the money that the money that flows in is linearly increasing with time. So for instance, this is the flow. At the beginning of the first year, when t is 0, it is at the rate of €1 per year, okay? But at the end, for instance, of year 5, when t is 5, it is at the intensity of €3 per year, okay? At the end of the 10th year, when t is 10, it flows in at the rate of €5 per year, and so on and so forth. So it is increasing linearly over time. However, we are discounting this flow at the rate of 5%. So what do you expect about the result of this? If this goes to infinity, now we compute capital T, but if capital T goes to infinity, you have a money inflow that grows linearly. So basically every year is 2/5 more compared to the previous year, okay? This is basically what the linear increasing function tells us. What do you expect about the present value? It increases linearly, but it is discounted exponentially. You may remember, I mean, the limits were part of the background for this course, but not of the course itself. But what prevails is the exponential factor. We discount the flow. It doesn't matter whether it increases. It increases linearly, so it has a weaker growth than the intensity with which it is discounted, okay? So what prevails is this one, so we will get a finite value as the integral between 0 and infinity, and we are going to compute it. This is a very, let's say, summary exercise, because there is integration by parts inside, and there is also the computation of a definite integral and an integral of an infinite horizon, in a case which is not trivial. Okay, we need integration by parts here. Okay, it's not, the integration by parts here is not really difficult, because just select g prime as usual as the exponential function. Okay, so this is g prime, exponential of minus 0.05t. What is g? We know this already from the previous example. G is a primitive of this one, which is minus 20 exponential of minus 1 over 20t. If this is f, we have just to take the derivative of f, and the derivative will be 2/5. So in the next step, I develop the formula to compute this integral by parts, and I just using these, say, ingredients that are ready here. When we have integration by parts, I don't remember if I told you this last time, but we saw examples of integration by parts with indefinite integrals. If we have a definite integrals, nothing changes except that you have step by step, to evaluate your quantities between 0 and capital T, okay? So basically this means that. Okay, so this is the formula for the integration by parts in general for an indefinite integral. Here is our integral, which is a definite integral between 0 and capital T. Okay, so the first part is f times g. F is again this one, and g, computed in the previous page, is minus 20 exponential minus 0.05 t. There is no more integrals here. This is already part of our solution, so we have to evaluate this between 0 and capital T. Okay, so this is ready for the final computation. But the point is that the second term of the integration by parts is minus the integral between 0 and capital T of what? The same g as above, this one, minus 20 exponential minus 0.05 t times f prime, which is 2 over 5. But now this integral is almost elementary because it is, this is plus 20 plus basically 80 plus 20 times 2 is 40 divided by 5, which is 8, okay? So this minus 2 over 5 times minus 20 is 8. So basically, in the next step, I evaluate this quantity between 0 and capital T, and I add just this integral written in a slightly better way. So this quantity becomes, this evaluated at capital T is minus 20, 1 plus 2 over 5 capital T exponential minus 0.05 capital T, minus the same quantity evaluated at 0, minus 20 is plus 20. This becomes 1 and this becomes 1. Okay, so plus 20. This is this part already written here as in the final solution. Plus this integral, but this integral is just 8 times an integral that we can compute because it is the same as 1 over.
Excuse me.
Yeah, please.
Excuse me, Professor. Could you repeat why we have plus 20?
Plus 20 because it is, remember that you have to take this quantity, compute this quantity when this t is equal to capital T, minus the same quantity, remember, minus the same quantity when t is equal to 0. Now, when t is equal to 0, here I have 1, this exponential factor becomes 1, so that would be minus 20, but we have to subtract this quantity, so it becomes plus 20. Okay?
Okay, yes.
Plus this one, okay, this one is 8 times minus 20, the same as above, so it becomes minus 160 exponential minus 1 over 20t, the red one, I'm computing only the red one here, from 0 to
Okay, yes.
Plus this one, okay, this one is 8 times minus 20, the same as above, so it becomes minus 160 exponential minus 1 over 20t, the red one, I'm computing only the red one here, from 0 to 20 minus 1. Okay, so the last part, the last integral is this one. Now, the last effort is to take the sum of this. I mean, the solution is already here. It's this one plus this red one. Okay, but we must try to write it in a better way, because especially if you want to compute then the limit as t goes to infinity. So let me take the sum of this one and this one in the next slide. So it is the sum of the first term, which is 20 is a common factor, times 1 minus this. Okay, 20 times 1 minus this one, plus this is the second term. Now 20 plus 160 is 180. Okay, and the other part as a common factor, which is exponential of minus 0.05t, okay? So I can factor the remaining terms, and here I have 20, or better, minus 20 times 1 plus 2 over 5t plus 160, okay? So basically, if you consider as a common factor here minus exponential of minus 0.05t, minus and the exponential factor here, you get this into the square brackets. So for instance, what happens with capital T equal to 10 years? This is, remember, this is a present value. It's kind of, you have a flow of money that lasts for 10 years. You want to compute its, let's say, price today, okay? It's a kind of, present value means exactly how much is it worth today, this flow, okay? This is the present value. It's, if t is equal to 10, our integral is equal to 180. Now capital T is equal to 10 here. This becomes 10 divided by 5 becomes 2. So this becomes basically 2 times 2 is 4 plus 1 is 5. So this is 100. So it's 260 exponential minus 0.5 because this is, it is this rate times 10. Plus 180, it becomes 22.3. So basically you have an increasing flow of money over 10 years. It flows at a rate that it increases over time. For instance, at the end of the 10th year, it is already it is at the rate of 5 euros per year. Okay, because when t is 10, this is 2 times 2 plus 1. It is at the highest point, the highest intensity of this rate is at the end of the period, and it is 5 euros per year, the intensity. Over 10 years, it starts from 1, but the total value, the total present value over 10 years is just 22.3 euros, okay? Because we are discounting. What happens to this as capital T tends to infinity? This is a quite important case, because here, in principle, we would say we don't know, because this part increases with t, but this part decreases with t. Which of them prevails? We have to compute the limit as t goes to infinity of this divided by exponential of 0.05t, okay? But when we have an exponential in the denominator and the linear function of t in the denominator, what prevails is the denominator that goes to infinity based on the theory of the limits. So the result of this limit is 0. So what is left is 180. So the present value of the flow is 180 euros. Even if the flow increases linearly forever, okay? But it is discounted exponentially. These are just examples involving elementary computations, basically, and an integral by parts, which is not that difficult to solve. We have alternative solution methods for this problem. One is if you don't feel really comfortable with using integration by parts and definite integrals at the same time, just compute a primitive using integration by parts. So just compute an indefinite integral, simplify as much as possible, and then evaluate it between 0 and capital T. So you can just try to do that, and then you get some indefinite integral, which includes a constant, and then you try to evaluate all of your results at the same time between 0 and capital T. You have to obtain the same as this one, of course, same expression as this one, the star. And another way is to break the integral into simpler integrals, because the integral between 0 and infinity of 1 plus 2 over 5t times this is just the integral of 1 times this which is elementary, plus 2 over 5 t exponential minus 0.05 t, okay? This is another, also the additivity property of integrals holds also in the case of definite integrals with an infinite time horizon, okay? With an infinite interval of integration. So whenever these integrals between a and infinity are well defined, whenever they make sense, they are really areas, let's say, all the additivity properties of integrals with respect to the function and with respect to the intervals of integration are valid, okay? So this is two alternative ways to compute the same integral, and I suggest to solve them. Point 1, point 2, to try to solve the same integral using these two alternative ways and to get the same result, of course. Okay. Before doing this, let me just show you. I remember that I left an exercise for you last week. So let me try to solve it for you. Did you try? Have you been able to solve? Were you able to solve this integral? And I guess that I left an exercise with two very similar integrals. So one was this one. So the integral of x times the square root of x plus 1, right? Dx. One was this one. And the other one was a somehow similar integrand, but it was x times square root of x squared plus 1 dx. Okay, so let me solve. Let me solve the first one. I regard x as f, and the square root of x plus 1 as g prime. After all, this is an elementary function to be integrated, okay? Because it's x plus 1 to the power of 1/2. I apply integration by parts. So this is equal to, okay, so my integral is equal to f times g. Okay, what is g? Is x plus 1 to the power of 3 over 2. Times 2/3. Because it would be divided by 3 over 2. And this is f times g minus g times f prime minus 2/3 times x plus 1 to the power of 3 over 2 dx. Just because f prime is 1, okay? This becomes equal to, let me rewrite first one, 2/3 x times x plus 1 to the power of 3 over 2 minus, this becomes 2/3 times, this becomes x plus 1 to the power of 5 over 2 divided by 5 over 2, so times 2 over 5. x plus 1 to the power of 5 over 2 plus c. It's really convenient to try to simplify this expression. For instance, I can isolate a factor here, which is 2/3 x plus 1 to the power of 3 over 2. Okay? 2/3 times x plus 1 to the power of 3 over 2 times what is left here? X minus 2 over 5 times x plus 1. Plus a constant. And this is just 2/3 x plus 1 power of 3 over 2 times. Okay, so x minus 2 over 5x is 3 over 5x. And minus 2 over 5. So this is the easiest way the solution can be written, of course. You see, it really comes out from the product of two functions, okay? So so here we apply a product rule. So basically here, if we want to compute the derivative of this, we apply a product rule. Then a lot of simplifications are possible, and what we get at the end is a relatively simple expression that can be integrated by parts, because it is related to the derivative of a product. But of course, there is no fixed rule for computing integrals. And the proof of this is that we can compute this integral also in a different way, very easy way, which is by substitution. I will show you something later. Can be computed also by substitution or change of variable very quickly, but also by parts is relatively easy. And the other integral is the integral, the 2 is integral of x times square root of x squared plus 1 dx, but now I can recognize the structure of the derivative of a composite function, because it is 1/2 times the integral of 2x times the square root of x squared plus 1 dx. So it is equal to 1/2. This is the derivative of x squared plus 1 to the power of 3 over 2, okay? Okay, so 1/2. Yes, it is this one. X squared plus 1 to the power of 3 over 2 plus a constant, okay? If you try to compute this derivative, of course, you get here 3 over 2 times x squared plus 1 to the power of 1/2, right? Is that correct? Yes. No, I forgot an important thing. I mean, it's x squared plus 1 to the power of 3 over 2 divided by 3 over 2, so 2/3 here. So it's basically equal to 1/3 x squared plus 1 to the power of 3 over 2. And you can check, just computing the derivative, you can check that the result is this one, okay? It is the derivative of a composite function. Now, before showing an example of integration by change of variable, okay, I want just to introduce, I just introduced to you the concept of integration by change of variable or by substitution. What is really important here is not using this as the solution of integrals that cannot be solved in any different way, okay, in any other way, but it's to show you the notation which is very likely you will find this notation in modeling, okay? Because very often we chase the variables, we have expressions involving integrals, and then we must be able to understand the notation, basically. So let me show you how it works. This is called integration by substitution. I repeat, what is really important here is the concept, the notation, not really the examples. But in some cases, it is also very useful to solve integrals. Suppose that we want to solve this integral, okay? I want to solve the integral of 3x over square root of 1 plus 2x squared. By the way, these are all useful exercises that I also solve in the traditional manner, okay? What is the structure of this integral? The structure except possibly a multiplicative factor. Okay, the structure is like this. It is structure of the integrand is g prime of x times g of x to the power of minus 1/2 dx. Okay? G prime of x would be 4x. Here we have 3x. Okay? But in fact, I write except possibly a multiplicative factor. And we can always adjust it. More generally, I want to arrive at the general formula. More generally, what is the structure? This is a power function, right? So the structure is of the type g prime of x times g of x to some power alpha, okay? This is the structure of the integrand in this example, okay? It is like this. More generally, it is like this. And even more generally, we have an integral of this type, the integral of a power function of a function g of x is only a function, a specific type of function of the function of g of x, okay? So it is an f of g of x. It is a function of g of x. So we have the integral of f of g of x times g prime of x dx. So this is the structure of these types of example, except possibly a multiplicative factor. Okay? In the specific case, now let me write what we do when we perform a change of variable, okay? This, it can be proven that this is equal exactly to the integral of f of some new variable u, f of u, du, where u is what? U is equal to g of x. Everything is consistent with the theory because the new variable is g of x is called u. So what is the differential of u? The differential is the product of the derivative times the increment of the x, the independent variable, okay? So du is g prime of x dx, it is here. This is du, this is f of u, okay? So basically, This means that we can rewrite the integral in the new variable u, but be careful. Here only variable x appears and dx. Here only variable u must appear and the differential must be expressed in terms of variable u, okay? So the new running variable is u, but u is not x, it's g of x. So the running variable here, the integration variable, is a new variable, okay? And it is related to the old variable by this. And this means that its differential is related to the differential of the old variable by this, okay? G prime of x dx is equal to du, okay? Oh, sorry. Okay? So basically, in the previous example, let me just conclude this. In the previous example, we would solve this in this way. So in the previous example, a naive solution, the one that we adopt, usually, because they are simple examples, recognizing the structure of a composite function inside the integral, okay? So the integral of 3x over the square root of 1 plus 2x squared dx is equal to, I would like to have 4x in the denominator, so it is equal to 3 over 4 times the integral of 4x over 1 plus 2x squared dx. And this is just basically, this is like 1 plus 2x squared to the power of minus 1/2. So it becomes 3 over 4 times 2 times 1 plus 2x squared plus c, which is equal to 3 over 2 square root of 1 plus 2x squared plus c. Okay? Now, if we want to use the change of variable, we have to do in this way. The integral of 3x times, divided by 1 plus 2x squared dx, I can select, there is no general rule for changing the variable. I mean, what we do here is to regard 1 plus 2x squared equal to the new variable u, so this is g of x. Okay? So remember that I must rewrite this integral in terms of u. So what is du? Du is equal to 4x dx. Okay? But now here I don't have 4x dx, I have 3x dx. So du is equal to 4 over 3 times 3x dx. Okay? It is the same as this one. But now 3x dx appears here. So 3x dx is equal to 3 over 4 du. Now, what we will do is to replace this. We become the square root of u, because u is the argument of the square root. And 3x dx becomes 3 over 4 du. So this is equal to the integral of what? 3 over 4 times 1 over the square root of u du. Okay? Now, this is an immediate integral, because it is 3 over 4 times, this is u to the power of minus 1/2 becomes 1/2 times 2, which is equal to, again like before, 3 over 2 square root of u plus c.
Aren't you forgetting the natural logarithm? Shouldn't it be ln of square root of U?
No, why, Alan? I mean, it's a power function. It's u to the power of -1/2. I mean, the integrand is not 1 over u.
Okay.
You can, the integral is the log only if you have a kind of, let's say, power function to be integrated, and the power function has exponent -1. For every other value of the exponent, you have a true power function, and you have to apply the rule for the power function, okay? But now remember that u is this, so it becomes 3 over 2 square root of 1 plus 2x squared, okay, plus c, which is exactly the previous result. We did the same thing, basically, but here we did it directly by recognizing directly the structure of the result of a chain rule inside the integrand. Here, we used kind of intermediate tool, which is the change of variable, okay? Just to transform, by the change of variable, here we have the derivative of a power function, of a function of x. So we have also its derivative. Here we have a power function of u. So it's an immediate integral. So by changes of variable, we usually transform our integral into a one which is easier to compute because it is an immediate integral. So let's take 15 minutes break now. Continue later. Okay, let's take a break now.
Devono chiedere, ma c'è un modo di
Maschera. L'anno scorso non abbiamo mai... Possibile.
Professor, may I ask you something, please?
Sure.
So it's an exercise about the derivative of an integral. In particular, it's this integral has extremes minus t and t, and the derivative is with respect to t.
Oh, minus t and t. Okay, but this is not one of my exercises because I didn't.
Okay, I found it on the book.
No, I didn't introduce, but the trick is as follows. Okay, so suppose that you have t only in the lower limit of integration, not in the upper. Okay, so you have, for instance, from minus t to 0, okay? Then in one of my slides, it is shown how to compute this integral because, I mean, I could, what about if I share my slides, can you see? I guess you should be able to see.
Yes.
So basically, suppose that you have to do something like this.
Now I cannot see them, sorry.
No, wait a minute. What about?
Yes.
Okay. Because if I just write, it's maybe better. Suppose that you, in one of my slides, there is an example like this, which is the integral between minus t and and b, because usually we call the upper limit b, okay, of f of x dx. Okay? By a property of the integrals, so what is the problem here? 6, okay. By a property of the integrals, this is equal to the integral between between b and minus t of f of minus the integral between b and minus t of f of x dx, okay? So you can exchange with one another the upper and lower limits of integration, and you get an integral which is the negative of the original integral. Okay? Can you understand?
Yeah.
This is not just t. This is a function of t. Not f. It's b of t. It's g of t. Okay? G of t. So to compute this integral, if you want to compute the derivative, so of the original integral minus t and b of f of x dx, you first have to transform this in order to have the quantity that depends on t as the upper limit, not the lower limit. So you transform this like this. Okay? Now, remember that this is a kind of g of t, it's not exactly t, it's g of t. And its derivative is minus 1. So it is minus, the fundamental theorem of calculus says that you have to compute f at the upper limit of integration. Okay, and this is the derivative, except that the upper limit of integration here is not exactly t, otherwise you just would have f of t, but it is a function of t, so you have to multiply them by the derivative of this function of t with respect to t, and at the end you have f of minus t. Okay?
Okay.
This is the derivative of basically your original integral. So you can compute the derivative between minus t and b of a function. Suppose that you have now the integral between minus t and t, some function. And you want to compute the derivative of this. The trick is only that of splitting the integral in two parts, for instance, by selecting an intermediate point between minus t and t, which is 0, provided that the function is defined there, okay? So you have the integral between minus t and 0 of f of x dx, plus the integral between 0 and t of f of x dx, okay? Now, by the fundamental theorem of calculus, you can compute this. And by my previous example, you can also compute this one. Okay? So you can, the derivative of the sum of two functions of t is just the sum of the derivative. So you can compute the first derivative, the other derivative, and then take the sum.
Thank you very much.
Okay?
I understood.
To split the integrals.
Thank you.
Welcome. So let me just recap the formulas for the integration by substitution in both the case of indefinite integral and also add the formula for a definite integral. So basically this is a summary. So in the case of indefinite integral, so the integral of f of g of x, g prime of x dx is equal to the integral of f of u du, where u is equal to g of x. Okay, and of course du is equal to g prime of x dx. And since so this is basically what we did in the examples, since this holds under certain regularity conditions of the functions, of course, but for differentiable functions having continuous derivatives, this is okay. And since this holds, we have a solution formula. So basically, the solution formula is that the integral of f of g of x, g prime of x dx is just equal to capital F of g of x plus a constant, where capital F is the primitive of lowercase f. That is, what is the meaning of a primitive? The derivative of capital F is equal to lowercase f. So this is basically the statement of the rule of integration by substitution, and what follows is the result. Okay, so we have a result here. Remember that this one, the last line, we did already without using the integration by substitution, because when recognizing the structure of a composite function here, we just arrive at the result. In simple cases, we can do that. In more complicated cases, we can do that by a change of variable first. Now, this is the main idea. But there is also a direct formula for definite integrals, and this is slightly, I mean, it's simple, but slightly more delicate one. You have to keep something additional, something more in mind. For definite integrals, so basically, if I have the integral between a and b of f of g of x, g prime of x dx, okay, this is again equal to the integral, some definite integral of f of u du with the same meaning of the symbols, but just keep in mind that since u is equal to g of x, here we have to put g of a as the lower limit of integration, and g of b as the upper limit of integration. And this is clear because here the variable of integration is x, and x runs between a and b. Okay? Here the variable of integration is u, but u is g of x. So what matters here is the range of function g, and u runs through the range from g of a to g of b. And by the way, depending on whether this function is increasing or decreasing, it may even happen that if a is less than b, but g of a could be larger than g of b, okay? So it depends on on the type of function here. Okay, so in this case, what is the solution? In this case, the solution is, so we use the change variable, but at the end of the story, the solution is that the integral of f of g of x times g prime of x dx is equal to capital F at g of b minus capital F evaluated at g of a, where again capital F is again a primitive of lowercase f. Okay, let me show you another example in which we have a definite integral. Sure, we could just do that. Example. Is the integral between 0 and 2, 3x times 1 plus 0.5 x squared dx. Okay? I select 1 plus 1/2 x squared equal to u. So this is my g of x. So du is equal to 1/2 times 2x dx. So it is just 1/2 times 2x is x dx. Okay? There are two more things. G of a, which is g of 0. What is g? Is this function, okay? At 0, it is equal to 1. G of b, which is g of 2, because b is equal to 2, is equal to 1 plus 1/2 times 4, so 1 plus 2 is equal to 3. So my integral can be written as the integral between 1 and 3. Now it runs from g of a to g of b, so from 1 to 3, of what? X dx is du, so here we have 3 du divided by u. Which is basically equal to 3. What is a primitive of 1 over u is the log of u. I can neglect the absolute value because u runs from u runs from u1 to 3, so the log of u is well defined. And we don't need the absolute value here because it is u is positive. From 1 to 3 it is positive. So it's 3 times the log of u from 1 to 3. Okay, so this is equal to 3 times the log of 3. Okay, so by exercise, just try to solve it without using the formal substitution. Just recognizing here the derivative of a composite function. And now a small issue comes out about the notation, because sometimes we don't have this simple structure with a number here and a number here, but we have a variable here. So now imagine that we have an original variable, okay? A variable which is the upper limit of integration. Another variable which is the variable that we use for the substitution. So be careful here, just showing you how what the correct notation should be. Suppose that we want to compute the integral. I use the same function as before, between 0 and t. Now the previous function is regarded as a function of time, okay? Is regarded as a function of time, and I want to compute the accumulated value between 0 and t. T is a variable upper limit of integration. So I have to first of all, I have to change the name of the variable of integration. I can call it u, okay? Any other name, y, I don't know, r, s. You can use any one. 1 plus 0.5 u tu. Suppose that now I want to solve this integral by substitution. If I want to solve this integral by substitution, I have to define a new variable. This was u squared, okay, not u, was u squared. I define a new variable for this expression. I can call it r. This is function g, how I call it g of u. I need a dr here. Okay, so dr is like my previous dx, or du is like my previous du as a function of x, okay? So dr is equal to u du, okay? Okay, now my integral is equal to what? The integral between g of 0, g is the function, g of 0, and now we have g of t. We don't have a number here, we have g of t, where g of t will be 1 plus 0.5 t squared, okay? From g of 0 to g of t of 3 over u, again, or if you like, you can call it 3 over r dr. But you don't need to call it r, I mean, okay, 3 over r dr, because this variable is a mute variable, okay? Is that clear? It's just a matter of notation, but don't get confused. So it becomes 3, primitive is log of r, and this must be evaluated between g of 0, and g of 0 is again 1, and the upper limit of integration is 1 plus 0.5 t squared. Okay, so the result is 3 times the log of 1 plus 0.5 t squared minus the log of 1, which is 0. Okay? I mean, if you're not, it is just a matter of notation, but understanding the notation means understanding the structure of what we are doing, okay? So this is g of t. Suppose that you want to compute the derivative with respect to t of this one, where g of t is g of t, 1 plus 0.5 t squared, okay? So compute the derivative between 0 and 1 plus 0.5 t squared of 3 over r, sorry, of the derivative with respect to t, sorry, of the integral between 0 and the upper limit of integration of 3 over r dr. What is this derivative? First, apply the fundamental theorem of calculus. So the derivative is in principle equal to the value of the integrand at the upper limit of integration, okay? The value of the integrand at the upper limit of integration. So it is equal to 3 over 1 plus 0.5 t squared, okay? It's the value of the integrand at the upper limit of integration times what? The derivative of the upper limit of integration with respect to t times 0.5 plus times to t. So it is equal to 3t divided by 1 plus 0.5 t squared, which is exactly the result. So, I mean, if we compute the derivative with respect to t of this, we get immediately 3t divided by 1 plus 0.5 t squared, okay? Based on the fundamental theorem of calculus. We change the variables. By changing the variables, this one is basically this, okay? It is the same integral. I only change the variable. So this integral is this. If I compute the derivative of this, I must obtain the same result as if I compute the derivative of this. In fact, the result is the same. I apply the fundamental theorem of calculus, but since the upper limit of integration is itself depends on t, I apply the chain rule by multiplying also by the derivative of the upper limit of integration. And you also obtain the same result if you compute the derivative of this one, which is the fully worked out integral, okay? So you always obtain the same result as the derivative. So it's not just notation. I mean, it's a structure that makes sense. Anyway, this is basically what I wanted to show you about this integral by substitution. And there is one more thing. And let me try to compute this integral. And this was computed by parts before, okay? So in principle, we can compute it also by substitution. I want to point out one thing. Integration by substitution matters for this course only for the notation. You must understand the meaning of this change of variable. And what is the new differential du as compared to the previous differential dx. Because this is also used to solve differential equations, for instance. So substitution is used to solve differential equations because we transform the differential equation into one which is easier, as an easier form, and we solve it. And we typically use substitution. So you must understand the meaning. For the computations, you don't need it because the computations, at least the ones I will submit to you for the examination, will be almost elementary. So you will easily recognize the structure of the chain rule, worked out chain rule inside the integrand, okay? So you don't need it. But remember that in practice, there are many cases of integrals that can only solve by substitution in the sense that there is no other clear way to solve them except trying to make substitutions and see what happens. See whether you are able to simplify these integrals. And this is one example in which, in principle, we can also solve it by parts, okay? But it is not immediate. Suppose that we want to solve it by substitution. There is absolutely no rule about which part of the integral to regard as the new variable, okay? This has a very simple structure. So in principle, we have two choices. 1 plus x is the new u, or the square root of 1 plus x is the new u. Of course, we try with the easiest one, okay? So let's suppose 1 plus x equal to u. By the way, this means that x that appears here will be equal to u minus 1. And also, this is g of x, du, which is g prime of x dx, is just dx. Because it is 1 times dx. What really matters now is that I can write this integral in this way, the integral of u minus 1, sorry, times square root of u, du. So this has been transformed in something that can be rewritten as the sum of two elementary functions, while this is not. You cannot reduce this to the sum of two elementary functions, but you can do the same for this one. You can do this. So this becomes the integral of u to the power of 3 over 2 du minus the integral of u to the power of 1/2 du, right? And this becomes 2 over 5 u to the power of 5 over 2 minus 2 over 3 to u to the power of 3 over 2 plus a constant. Then you can, for instance, identify a common factor here just to write it very quickly as the result of the previous integral by parts. Just select this as the common factor. So 2/3 u to the power of 3 over 2. So this will become -1, okay? And what about this? It is u, because you extract u to the power of 3 over 2. It becomes u, and if you have to divide by 2/3, so to multiply by 3 over 2, okay? 2 over 5 by 3 over 2, it's 3 over 5. U minus 1, okay? Clear? Now remember, plus c, of course. Now remember that u is 1 plus x. So we have 2 over 3, 1 plus x to the power of 3 over 2 times 3 over 5, 1 plus x minus 1 plus c equal to 2/3 1 plus x power of 3 over 2. This is 3 over 5 minus 1, it's minus 2 over 5. So 3 over 5x minus 2 over 5, which is exactly the result of the same integral by parts. So, for instance, this is one case in which, I mean, it is not so easy to understand here the structure of the derivative of a composite function, okay? But if we try with changes of variables, we may discover that, in fact, this is the derivative of something that involves a composite function here, because here we have, you see here we have this composite function of 1 plus x. Can you see it? But it's very complicated. So the point is that when you compute the derivative, you can simplify a lot of things and you get a structure which is so simple that you can't understand, can't realize anymore that that was the derivative of a composite function, okay? In that case, we have integration by substitution that helps a lot. But it's not, I mean, it's not necessary for our examination. If you can do it, if you can use it, there are some cases in which it may be useful. Okay. Just going to go back to this slides, which was, this is some material that you already have. I have uploaded it. There are additional exercises. So, for instance, this one, it is already in the slides, but I want to repeat the exercise here. Okay, this exercise is already in the slides, but let me repeat the exercise because I think that our, ability to concentrate on mathematics is vanishing now, tends to 0. Also mine. So let me just writing it again, step by step, by just changing the names of the variables. Suppose that I want to compute the integral between 0 and capital T of t times the exponential of minus beta t squared dt, where t is the time horizon, strictly positive, and so it's larger than 0, of course, and beta is some parameter which is positive as well. By the way, remember that you can also solve this by substitution. I suggest that you try to solve this by substitution, because you see the structure, it is exponential of minus a function of x of t times its derivative, apart from a multiplicative factor. So what would be the exact derivative of minus beta t squared? It would be minus 2 beta t. And here I just have t, okay? So this is equal to minus 1 over 2 beta times the integral of minus 2 beta t exponential of minus beta t squared dt. So it is minus from 0 to capital T. It is minus 1 over 2 beta. A primitive is exponential of minus beta t squared. From 0 to capital T. 2 beta here. Which is equal to minus 1 over 2 beta times exponential of minus beta capital T squared minus 1. But this is less than 1, so this is negative. This is also negative. Let's make both of them positive quantities. 1 over 2 beta times 1 minus exponential of minus beta t squared. Okay? What about the integral between 0 and infinity of the same? It is just equal to 1 over 2 beta. Because when I take the limit as capital T tends to infinity, this one tends to 0. And we are only left with 1 over 2 beta. So this is another simple example of the simple composite function. And it is already here, just the name of the variable is x, not t. The upper limit is called k and not capital T. And then we have the limiting behavior as the upper limit tends to infinity. So I think that should be enough for today. Okay, so basically the part on integrals is here. So let me just recap. We have elementary integrals. What is the meaning of elementary integrals? Power functions, x to the power of alpha. Positive, negative. In particular, alpha equal to minus 1. The integral is the log in that case. Exponential functions and power functions, okay? These are the elementary functions. Next, we have another step, which is elementary, which means power of exponentials, not of x, but of a linear function of x, okay? This is the next step. The rules are almost the same as the ones for elementary integrals. Next, we have simple structures of derivatives of composite functions in the integrand, possibly to be adjusted with constants, and go back to the original composite function by computing the integral. In some cases, integration by substitution is useful here. Next, integration by parts, in which cases, basically, the most important cases are products between elementary functions, in particular x and some exponential of x, of alpha x, of minus alpha x, and so on and so forth. Another point is the fundamental theorem of calculus and being able to compute the derivative of an integral with respect to the upper limit of integration. Also, when the upper limit of integration is not x, but it is a function of x, in which case we have a chain rule. We can extend this also to computing the derivative of an integral with respect to the lower limit of integration, just because I can rewrite the integral in a way that the variable doesn't appear anymore in the lower limit of integration, but in the upper limit of integration, okay? So this is basically what we learned about the integrals. And another thing is integrals extended to infinite intervals of integration. From zero, typically from 0 to plus infinity, or from some positive number to plus infinity. Okay, so this is basically what we need, and these are elementary integrals that are highly needed to solve differential equations. We will start tomorrow with the differential equations. Tomorrow I will start with differential equations that do not actually require particular abilities in solving integrals, except the integral of an exponential, which is the exponential itself, basically. But when we will deal, for instance, with so-called separable equations, then we will need these kinds of elementary integrals and almost elementary integrals, and also understanding the notation of integration by substitution. Understanding the notation, at least. So I think that's all. See you tomorrow.
I'm sorry, general question. Do you know more or less when the grades?
Yeah, the results of the, okay. What do you expect? Okay, no, it takes at least 1 week.
Okay.
I'm so sorry for that, but in this period there were many more administrative duties to be fixed in the past 2 weeks. So I started already, but I need more time, because then I have to compare them once more and to decide the final grades.
Okay. Thank you very much.
Thanks. Okay, see you tomorrow. Bye.